Yo, week 2, Q4, lesson 2. Let's do it. Hopefully my lesson's better than what I look like right now. I feel like a visual personification of quarantine. You know, man. Just wanna go outside. I mean, I can do that, but just wanna go to school. Anyways, here we go. 2 sample t-tests. Let's rock. So yesterday we started looking at 2 sample t intervals, estimating the difference in 2 population means, 2 mu's, based on 2 sample means. So we used our interval yesterday to try to decide. We could, one, look at, is there a significant difference in the mean wait times of males and females at the coffee shop, right? And we look for 0 in the interval because that represents no difference. We could also use our interval to try to make a decision about, do we think one mean wait time is significantly larger than the other? And we talked about how we could do that focusing on the positive or negative signs of the interval. So today we really want to look at another way to address those same questions. Is there a significant difference in 2 means, or is one mean significantly higher than another, using a hypothesis test and ultimately basing our conclusion on a p-value? So as you jump in, context-wise, same exact context as yesterday. So pick up where yesterday's video left off in your notes. But if this is new, maybe a good idea to write this down. So we're looking at comparing the mean wait times of males and females at a coffee shop in Boston. And today, right, the question is there statistical evidence? And so as we look at this, the statistical evidence phrase kind of suggests to us exam-wise that might be a hypothesis test, but that the mean wait time differs for males and females. And if by here we don't know that this is a hypothesis test, the 5% level of significance hopefully makes that super obvious. So we should know that we're going to have to do some kind of hypothesis test for this. But then the question comes up, like, what kind of hypothesis test do I use? How do I figure that out, right? Because now we're starting to build a larger bank, and that's something we'll practice, either at the end of this week or start of next week. So as you think about it, right, again, the evidence alpha level, we know that it's going to be a hypothesis test. Then from there, we have 2 samples, so that narrows it down. It's either a 2 proportion z-test or a 2 sample t-test. And then from there, since we're working with means, that's how we know it's t. So that's the logic you want to walk yourself through as you're trying to figure out what type of test or interval to use, right? First, is it a test or interval? Then, do I have 1 or 2 samples? Then, means or proportions. And that's how we ultimately can arrive at the type we're going to use. This is my little table summarizing our data. We saw that yesterday. So as we go about this, right, same process as always: hypotheses, conditions, math, conclusion. And I challenge you to pause the video right now. I'm pretty confident you could do that. It's really similar to the 2 prop z-test. We're still going to assume no difference in the null. And as I get into that, right, still going to use those same conceptual ideas. It's just, instead of writing about 2 p's now in our null and alternative, now we're going to write about some mu's, right? A mean for men and a mean for women in this case. So try that out. Forgot my pause symbol. Pause. Happy face, pause. And hopefully you wrote something like this. We got a couple ways we could write the hypotheses. So my personal preference is here, and you could either use M's and F's or 1's and 2's. If you do use 1's and 2's, we need to have a key as to which group is which. That's why I like this table. This table serves as that key and helps me summarize my info, and my calculator is going to have a bunch of 1's and 2's. So personally, I like to keep track of it that way, but we can also use the M's and F's. So if you can just kind of mentally keep track of which one is the 1 or which one's the 2, or maybe even just do that, write the 1's and 2's above them so you know which one's which. So we can write, right, we're assuming no difference. We're assuming the mean wait time for men and women are the same, or the mean wait times for men and women are the same. Another way to write that, if the mean wait time for the men and the mean wait time for the women is the same, when we subtract, we would get 0, right? We're literally assuming there is no difference in our proportions. And in this case, we want to know if there's evidence of a significant difference, right? So the mean for the men is just different than the mean for the women. Or if they were different numbers, when I subtract the mean for the men minus the mean for the women, I would not get 0, right? So a couple options for how you can write these. I personally prefer what's on the left. Whatever, you do what works for you. So that's our hypotheses. Conditions-wise, same as the interval, right? Nothing we assume in our null, right? There's no mu's used anywhere in the condition, so that null assumption is not going to affect anything condition-wise. So same exact situation as the interval, 10% condition for males and females, random samples, large enough samples for each group, and independent groups. So if you haven't done that with the previous video, go ahead and do that now. And then hopefully you're writing down something like this. No big deal here. You can pick, pause and kind of read through. And the black is just showing a different way you might write each condition. I would personally write the blue, right? But the black is another way to word each of those conditions. So then we get to the math. Anytime you're going to the math, you're going right to your calculator. So you're going to do the 2 sample t-test on your calculator, write down the name at least, test stat, and p-value. The other stuff that's there, the x-bars, the s-x's, we're going to use those in writing in the degrees of freedom in the t-score formula. That's something I should make sure we write down here, right? Degrees of freedom. And then we can also use the draw feature to look at a sketch. So as we do that, hopefully you're entering all this in our summary stats. There's my stuff for the men, my stuff for the women. We're always going to choose no for this pooled option for any of the 2 sample T stuff. And then we get this output screen. So we want to make sure we have the name, the T-score or standardized test statistic, the p-value, and the degrees of freedom. I'm going to use these numbers. And if I scroll down, it would just show me the 2 ends. I'm going to use these and the 2 ends in the T-score formula in a moment, showing how this T-score of -3.77 is calculated. Another little side note, keep in mind that the p-value is the probability. Right? The probability we see this sample difference if it were true that there were no difference in mean wait times for men and women. So that's got to be between 0 and 1. So don't make the mistake of writing 2.04. Right? This means we have to move the decimal 4 places to the left. So we're going to have 0.0002. So you could already, right, p-value 0.0002, you should already have some thoughts about what the conclusion is. And if I were doing a free response on the exam, I'd probably go ahead and write the conclusion based on this p-value, sloppiest stuff ever written, right here, right? Hopefully you're thinking about if you're going to reject or fail to reject, there is or is not evidence, all that stuff, right? So definitely can jump right to the conclusion in real life. Like, well, I guess this is real life, but you know what I mean, like on the test. But formula-wise, so let me hop over to the whiteboard here. I apologize for the shadow. It's my first time doing this in the evening. So now this is a little weird. So our standardized test stat, that's a Z or a T score. And the reason I was gonna say it's a little weird is in a normal school year, I'd be talking about how this formula is given on the AP exam formula sheet, right? So it's our statistic minus our parameter over the standard error of that sample statistic or statistics. And additionally, this standard error formula is also separately given on the formula sheet. But we're in a weird situation this year, as we know. So there's no formula sheet that's going to be handed to you. So like you use whatever notes you want, like maybe this right here. So for any Z or T score, our statistic, that's based on our sample. Now, what's a little weird here, it's not weird, I guess it's just different than last week, is we don't just have one sample statistic, we have 2, right? We have the mean for the men, and the mean for the women. But hopefully we know that anytime we do have 2 sample statistics, we're always going to focus on the difference in those. So for me, I got 85.2 minus 113.7. Something to think about here is on the calculator, the T-score was a negative number, so this should be a negative difference, something to keep in mind. If I wrote this in the other order, I'd get a positive difference that would not match my T-score, and as a result would be incorrect. So that's what's up with our statistic. Our parameter is always based on the null hypothesis. So we're focusing on the difference in means, remember? And in the null, we always assume no difference, and that's why this is a 0. So of course, if you didn't write that, that's not a big deal, but conceptually, that's where that's coming from. And then lastly, for the standard error, we saw this reference with the interval. This is based on that idea that variances always add. So with the standard error, in a normal year, I'd say this formula is given on the formula sheet, square root sigma 1 squared over n1 plus sigma 2 squared over n2. Right, so this formula would be given, but again, this year we have our notes. We don't have sigmas. If we did, we'd be doing a 2-sample z-test on a side note. We use member T whenever we don't know the population standard deviation sigma, which is what's going to happen more often. Here we have sample data. That's why we're using T. So our sample standard deviation, so we're going to have 50 squared over 145. and 75 squared over 141. And so this is how that t-score of negative 3 point whatever it was is calculated. All right. So that's it for the math here. Now, a little more about the math. I want to take a peek at this picture, just refresh our memories on some stuff. And so you could, right? I already mentioned, right? You could write the conclusion, same deal as always, right? And that's what I would do. But jumping back to the picture. So when we go to the model, you don't really see it on the calculator. Remember, the t-distribution does have fatter tails, but in this case, we did have 243 degrees of freedom. So that's why this looks so much like a normal model. Because, right, remember, as degrees of freedom increase, the t-distribution has less variability and looks more like that bell curve that we envision. If the degrees of freedom were like 5, then we'd see, right, maybe not that drastic, but some fatter tails here. Also, that's the worst picture ever. So, a couple of things to point out. Like, you might be wondering, like, why don't I see anything? And hopefully we realize that's because the p-value is incredibly small. Remember, visually, we're shading, theoretically, 2 tails because the alternative was not equal to. But this is how much of the picture we're shading. So we're shading 0.0002 or 0.02% of the picture. And so that's why we don't really see anything. If we did, it would be the 2 tiniest little slivers because we're shading almost none of this normal distribution. Oh, I did it, right? It looks like it, of this t-distribution. If we were going to label, right, we're assuming in the middle here, we're assuming no difference in our sample means, and we would mark and shade our t-score of negative 3.77. That's a pretty bad job of negative 3.77. It's negative 1, 2, 3, 4. Notice that this does show more than 3 standard errors above the mean, and that's because, right, it's hard to see when they're not on the same scale. That's because the t is more spread out, right? So the normal model, the z stuff on our calculator only shows us from here to here. And so we can kind of tell that this is a little more spread out, although we don't see like drastically fatter tails. Anyways, this t-score of negative 3.77, this would be from doing that 85.2, the actual sample difference minus the 113.7, right? So you could get through a free response and actually write a conclusion without all that, right? But, you know, just try to understand what we got going on here. All right, conclusion, nothing new there. You know the deal. P is lower than alpha, reject the null, blah, 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 blah. Write that down, and then hopefully you wrote something like this. P-value is below alpha, so we're going to reject the null. There is evidence that the mean wait time differs for males and females. Decision, reject or fail to reject. Linkage, connect your out p-value to an alpha level. Context, there is or is not evidence. And remember, there is or is not evidence. We're always commenting on the alternative hypothesis in context, which is typically going to be something we can just copy that wording right out of the context that's given to us on the exam. So before we wrap it up, a couple questions for you guys to think about. So first off, think about this. What if this were the alternative hypothesis? So 2 questions based on that I'd like you to think about. If this were the alternative, 1, what would the question have to be? What question would have us rewrite this alternative hypothesis, right? Not is there evidence that the mean wait time differs for males and females, right? What would that have to say? And then 2, if we change the question so that this were the alternative hypothesis, would our decision change? Would we still reject, or would it now become fail to reject, and why? How could you explain that? And pause and like, but like, I'm not gonna do the whole thing. And hopefully came up with these brilliant ideas. Like, I'm not gonna read that. You guys can just pause the video and read that. Right, read that yourself, right? This would mean that the mean wait time for women was longer. If we were going to get a negative, right? The only way this would be a negative difference is if this wait time for women was longer or larger. And then, you know, read stuff. A couple more for you. Next one. Good old friends, types of error. Can you define each type of error in context? Remember our little template, in reality blank, but our test suggests blank. Type 1, the first one is true. Type 2, the second one is true. And when I say that, right, I think about these as the first and second hypotheses. So try to define your types of errors. talking about differences or not having a difference in mean wait times for males and females. And hopefully you wrote, boom, that. I like to use that template in reality, but our test, so we can distinguish, between what the reality is, which is not something we would really know, We only know what our test, what our data tells us. So we don't say things like there's not a difference, but there is, and that makes no sense. Last, maybe, I don't even know, the power of the test. So it's been a long time. This is what we were looking at right before we got cut off for distance learning, talking about power. So in general, power is the probability that test correctly rejects the false null. Go back to the courtroom. Power is the probability we convict someone who's actually guilty. If we reject the null, we determine a person was guilty, and if the null was false, that would mean the person is actually guilty. So power is a good thing. We want our test to have high power. It's the probability we diagnose someone with COVID if they actually have COVID, Thinking about what's going on, So we want 100% power, Unfortunately, our statistical tests aren't perfect. So really, I like to try to use this definition and just fill in the blanks. So in this case, think about what would we conclude if we rejected the null? And in reality, what would it mean if the null were false? And then hopefully we got something like this. So the power is the probability that our test correctly determines there's a difference in mean wait times if there is in fact a difference in mean wait times at the coffee shop for men and women. All right. Practice, man. I know this is hard, guys, and I know I'm asking a lot, kind of, but come on. We're better than our last assignment's completion rate. So let's just keep getting through this together. Don't be lazy. Grade your free response. Pay attention to the details. Write detailed, because you're going to take the exam, The answers on your exam are going to look like the ones you write at home. You play how you practice, no matter what you're talking about. So step it up. Practice hard. I'm always here if you have questions. I miss you guys. I always say that and then forget I have to stop share. And see you in Zoom soon, I hope.